Hello everybody. We started our lecture. It's lecture number 7. And today we will discuss existence and uniqueness of the solution of a differential equation of the first order. Existence, right? And uniqueness. Of the ordinary differential equation of the first order. So it will have the form y prime equals f of xy. So we have already discussed singular solutions and non-singular solutions, and now I want to discuss this problem, the theorem on existence and uniqueness of a solution. Okay, so we will start with the differential equation y prime equals f of xy, where f of xy is a continuous function. On a rectangle, it will be given by hello. So we will consider an initial value problem, and so we will start. Hello, welcome. No quiz, no quiz.
I'll come back after.
Right. You may do this. No quiz. So, we will consider the initial value problem. So we will require y of x0 equals y0. So we will consider this differential equation, this initial value problem, and so our rectangle should include the point x0, y0. It should be the following: x0 minus a, x0 plus a, and y will be between minus b, y0 plus b. So our point, our initial value should be inside the rectangle. I will draw the figure. So let it be x0 and y0. This is our point. And suppose our function is continuous inside this rectangle. This rectangle should be included in the domain of the function, and the function is continuous. Okay, so our function can be defined outside this rectangle. So this will not contradict our theorem. So our theorem will be considered, all the properties of the function will be considered inside this rectangle, but the function may be or may not be defined outside the rectangle, or it may be continuous. It doesn't matter, right? So we will consider a rectangle. And so the other properties of f of xy will be assumed, and now I will state theorem. It is called existence and uniqueness theorem. Okay. So it states that if the function f of xy and its partial derivative df over dy are both continuous, in the rectangle are specified. So I will recall that R is the following. Okay, then there exists, so there is H, a positive number between 0 and A, such that our differential equation f of xy has okay, so initial value problem. So y of x0 equals y0 has a solution. I will call it phi of x. So the function phi of x for x between x0 minus h, x0 plus h, and this solution is unique. This is the only solution okay, so and y, just a moment, y0 minus b, y0 plus b. And this is the only solution okay, for x between x0 minus h and x0 plus h. So this is a theorem. I will draw a figure. So we have a large rectangle with x0 and x0 minus a, x0 plus a. And inside this rectangle, there is a smaller rectangle in which we guarantee the existence and uniqueness of the solution of our differential equation. So this is the center of our rectangle. y0 minus b. This is y0, y0 plus b. And our theorem states that if inside this rectangle our function and its partial derivative with respect to y are both continuous, then there is a smaller value h. H should be less than a, and so a smaller rectangle such that inside this rectangle, inside this smaller rectangle, our differential equation has a solution, and this solution is unique for x between x0 minus h and x0 plus h. Okay. Well, and now we will I want to prove this theorem. So the proof of this theorem is very complicated. So the proof of existence is very complicated, and I will leave the proof of the existence without proof. We will omit the proof of the existence, but we must discuss the proof of the uniqueness. So this is an important theorem, and we will refer to this theorem in what follows. So I should do this. And first of all, so our lecture will be devoted to discussion of this theorem. And first of all, I'd like to discuss the complexity of this theorem. So there are several requirements, and I want to discuss why these requirements are so important. And the first problem, the first question is why H is important. Why can't we guarantee the existence and uniqueness of the solution inside the original rectangle? And so we will discuss this. Maybe I will leave this just a moment. Let it be the figure. So x0 minus a, x0 plus a. So the first question is, why can't we guarantee the existence and uniqueness of our solution inside the original rectangle? Why should we choose h which is less than a? Why a is not enough? So our function is well defined, it is continuous, and its partial derivative is continuous inside this rectangle. Why should we choose h which is less than a? And so to answer this question, we will consider an example, example number 1. I'd like to consider an equation of the form 4x times y plus 1 squared, x of 0, so y of 0 equals 0. So this is an initial value problem. Okay, so look at the function. So our function f of xy is equal to 4x times y plus 1 squared. And we can see that this function is continuous in the entire plane. R2, and its partial derivative, let's find its partial derivative. It will be equal to 8x times y plus 1 is also continuous in the entire plane. So we are free to choose a rectangle as we want. So for example, in our case, I want to set a to be equal to 1 and b also to be equal to 1. So let's consider this rectangle. So this is an origin, the origin, and we consider the rectangle between 1 and minus and negative 1. So this one. This is a square inside this rectangle. And now we want to see why we can't choose h to be equal to 1. Let's try to use this theorem. Let's solve this differential equation. So this differential equation is separable, and it can be solved explicitly. And we can see, we can find the exact equation of the solution of this differential equation, and see why h is should be less than 1. Right? Let's solve this. Okay, so dy, step number 1 to solve the equation. 4x times 1 minus plus y plus 1 squared. So this is dy over y plus 1 squared equals 4x dx. Then we have minus 1 over y plus 1 equals 2x squared plus c. And since we seek the initial value, since we're solving the initial value problem, so we seek the solution satisfying this condition. Then we have the following. We should substitute 0 for x and 0 for y in this equation, find c. Let's do this. So we have minus 1 equals c. So c is negative 1. Well, and so I will continue this way. So we have minus 1 over y plus 1 equals 2x squared minus 1. Then invert this equation and we will get y plus 1 equals 1 over 1 minus 2x squared, and y equals 1 over 1 minus 2x squared minus 1. It will be 2x squared over 1 minus 2x squared. So this is our solution. And if we try to draw the graph of this solution, we will have the following. So there are two asymptotes. X equals plus or minus 1 over root 2. Look at the denominator. It vanishes when x equals plus or minus 1 over root 2. So we can see that our function blows up when we go close to these vertical asymptotes, these values of x. 1 over root 2 and minus 1 over root 2. And the graph of this function will look like this curve. And we can see that in spite of the fact that the function is defined, so look at the original equation. So our function is continuous and its partial derivative with respect to y is continuous on this rectangle. So I will draw it here. So it is 1 over root 2 and 1 should be here. So it's this rectangle. Minus 1, 1, and 1. So the function and its partial derivative are both defined and continuous in this rectangle. But if we want to guarantee the existence of a solution and uniqueness of a solution, we should choose h to be less than 1 over root 2, right? H should be less than 1 over root 2. So this is a necessary requirement, and look at the theorem. So it states that there is h between 0 and a, right? So this is necessary. The second discussion, so this is example 1, and we have discussed the importance of h. And next I want to discuss the uniqueness of a solution. And we will find a necessary condition among these requirements imposed on the function f, right? So I will emphasize the importance of other requirements in our theorem. Like now, example number 2. And I'd like to consider a differential equation y prime, which is equal to 3y raised to the power 2/3 and y of 0 equals 0. This is an initial condition. Let's try to solve this equation and discuss the uniqueness of a solution of this initial value problem. Okay, by inspection we can see that y equals 0, identical 0 is a solution, right? Because if we substitute identical 0 into the equation, it will be satisfied, right? The derivative is 0, and so the left-hand part, the derivative is 0, and the right-hand part is also 0. Well, now let's try to find other solutions. And I'd like to show that the solution is not unique. Well, dy over dx equals 3y to the power 2/3. We can solve this equation by separating variables. It will be dy over 3y to the power 2/3 equals dx, and then integrate both parts. This integral is equal to y to the power 1/3 equals x plus c, and so y equals x plus c cubed. Okay, given this initial condition, we can find c, and c is equal to 0. So we have found another solution, y equals x cubed. This function also satisfies the original differential equation, right? Let's prove this. Let's verify this. Then y prime, so if y is x cubed, then y prime will be 3x squared, and 3y to the power 2/3 will be 3 times x cubed to the power 2/3. It is equal to 3x squared, the same. So this function will also satisfy this initial condition. So there are at least two functions satisfying this differential equation with this initial condition. Okay, will it contradict our theorem or not? Maybe theorem is wrong. So identical 0 and x cubed and if we fix a neighborhood, so if we fix h minus h and h, we can show that there are infinitely many solutions and infinitely many functions satisfying this differential equation for x between minus h and h, because the family of the integral curves will have the form this. This is the family of curves. Okay, and except for these two solutions, identical 0 and x cubed, we have infinitely many solutions. They look like, so we may start with any curve. For example, we may start from here. Next, we may go along, go along the x-axis. Okay, and next we may end our motion using the other curve, right? So there are infinitely many solutions. Okay, does this contradict our theorem or not? Let's check all the conditions of the theorem. So f and the partial derivative with respect to y should be both continuous in some rectangle. Is this requirement satisfied or not? So very simple requirements, right? F, so what is f? It depends on, it is 3y to the power 2/3. It's continuous in our, so in the entire plane. It doesn't depend on x, and it is continuous in the entire plane. What about the partial derivative? Right, it is 2 over y 1/3. Right, is it continuous? Okay.
Where y is equal to 0.
Right, it is not defined, it is not continuous, and it is even not defined at 0, right? Okay, so this requirement is also important. Partial derivative of f with respect to y should be continuous, and we will use this in our proof. Now I'd like to prove the theorem. So we have considered two examples, and we have discussed the formulation, the statement of our theorem, and now I will prove uniqueness. It is easier than to prove existence. I will omit the proof of the existence, but uniqueness will be discussed now.
So does that mean in this rectangle you drew here?
Here.
Does that mean there's only one solution?
Right, only one solution. So it's okay. So this function satisfies the theorem. This is only about. So this is merely about the problem of choosing h. Okay, so I have discussed that the function is defined and continuous in the large rectangle. Why should we choose the smaller rectangle? To guarantee their existence and uniqueness. So this is only the problem. So it's okay with the uniqueness and existence, but h should be less than 1. So h should be this. So if we choose h to be less than, in this rectangle, the solution will be unique and it will exist, right? I need space to prove, and so it's not easy, but it is more easy than prove the existence. Because to prove the existence, we should construct something. Now we may assume that that a solution exists. We will assume that two solutions exist, and we will prove that these solutions are the same in some rectangle. Okay, proof. Of the uniqueness. Okay, I will need several statements, and I will state them separately, right? I will prove a lemma, and I will recall some facts from calculus that are needed to prove our theorem. So I will start with lemma. Okay, so if the function is continuous, then any solution suppose the solution exists, any solution of the differential equation will satisfy the integral equation. So it is, just a moment, I mean initial value problem, so I must include the initial value problem here. So it should be y of x0 equals x0 will satisfy okay, phi of x will be equal to the integral. So in just a moment, it will be y0 plus the integral from x0 to x of the function f of x, f of s. I will use another variable. ds. And conversely, if the function satisfies, if the function phi of x satisfies this equation, then it satisfies the differential equation. So, and conversely. Okay. Let's prove this lemma. I will prove it. First, suppose, okay, if it's continuous, then any solution will satisfy. Okay, suppose phi of x is a solution of this differential equation, and let's find the, okay, let's consider this integral equation, and let's differentiate the right-hand side. Let's find the derivative of the right-hand side. Okay, since our function f is continuous, then by the fundamental theorem of calculus, this derivative is equal to, so y0 is a constant, right? And so the derivative is equal to, it is equal to f of x phi of x. And the derivative of f prime of x also equals f of x phi of x, because phi of x satisfies this differential equation. Okay. And we can see that phi of, so the derivative of phi of x, so the derivatives of both sides of this integral equation are the same. And in addition, we can see that phi of x0 equals y0. If we substitute x0 for x, we can see that this integral is 0, and so phi of x0 equals y0. So this proves, this is the same, so this is the initial, just the initial value problem. And so we can see that if our function phi of x is a solution, that it will satisfy this differential equation. Conversely, if phi of x satisfies this integral equation, then if we differentiate both parts, we will get this equality, phi prime of x equals f of x and phi of x. Okay, and so if phi of x satisfies this integral equation, it will satisfy this initial value problem. So the lemma is almost trivial, and we will use it in what follows. And except in addition to this lemma, we will need some other facts from calculus. The second fact, so this is the first fact. The second fact that will be used in proving the theorem is the following. So since the function df over dy is continuous in the rectangle, this is bounded and closed set, then by extreme value theorem, it takes on its maximum and minimum values, right? So there exists, call it L, which is the maximum of the absolute value df over dy over this rectangle. And so we will use that the absolute value of this function is bounded on the rectangle. Well, next, fact number 3, we will use the Lagrange mean value theorem. For derivatives. Okay, it states that if the function f, okay, so now we will fix x. For this, we will fix x. And we will consider our function f depending only on one variable y. So since f of y is continuous and differentiable, is continuous on y0 minus b, y0 plus b, and differentiable so and f of y, so f of y is differentiable y0 minus b, y0 plus b, then for any two points y1 and y2 from this interval, there exists a point y asterisk between y0 and between y1 and y2, such that df over dy at y equals, sorry, just a moment, it will be f of y1, for example, minus f of y2 is equal to the derivative taken at this intermediate point times y1 minus y2. And since this is bounded, look here, this function is bounded, then we can state that the absolute value of f of y1 minus f of y2 doesn't exceed L times the absolute value of y1 minus y2. Okay, and this is true. So x was fixed But now we can see that this is true for any x, right? For any x from our rectangle. So x between so for any x from x0 minus a, x0 plus a. Okay, we will use these three facts in proving our theorem, and now we will try to prove. Well, I will start to use this part. Okay, these are preliminary facts, and now proof. Okay, so we will assume that there exist two functions. So suppose two functions exist, phi1 of x and phi2 of x satisfy the differential equation. So, and phi2 prime of x equals f of x, phi2 of x, phi2 of x0 equals y0. Okay, we will try to find the difference. Phi2 of x minus phi1 of, or maybe let it be 1, because I have used 1 minus 2, so let it be 1 minus 2. The difference of functions. So first of all, we will apply the lemma, which was proved before, this one. So each function satisfies this integral equation, and we will use this formula. This is the first step, to use this formula. So phi1 minus phi2 will be equal to so y0 plus the integral from x0 to x of f of s phi1 of x dx minus y0 plus the integral from x0 to x f of s phi2 of s ds. So y0 is cancelled out, and we can collect the functions. We can use the additivity of the integral and write this difference as the integral f of s phi1 of s minus f of s phi2 of s ds. Okay. Well, now I want to estimate the absolute value of phi of x minus phi2 of x. Okay, I will need one more fact from calculus. It was 2, 3, and fact number 4. So there is enough place for it. Fact number 4. If we have a function which is Riemann integrable on some, let it be the closed interval from x1 to x2, if it is Riemann integrable, then we have the following equality. The absolute value of the integral from x1 to x2 of f of x dx is less than or equal to the integral of the absolute value. And now I'd like to apply this formula. So the absolute value is less than or equal to the absolute value of x0 from x0 to x of the absolute value of f of s phi1 minus f of s phi2 ds. So this is by 4, and now by fact number 3. By 3, we can write that this is less than or equal to the integral from x to x0 to x of L. So by this inequality, it is less than or equal to L times phi1 of s minus phi2 of s ds. Now, okay, so for simplicity, I will consider in my proof, I will prove the uniqueness. So I will the uniqueness for x which is greater than or equal to x0, x greater than or equal to x0. And I will choose h a little bit later. But we will suppose that x is between x0 and x0 plus h. And so this can be estimated. So this is not exceed the integral from x0 to x0 plus h. H will be chosen later. L times phi1 of s minus phi2 of s ds. Okay. Now I need space, so I will clean this part of the blackboard. Well, I will move here. Let's introduce the norm. The norm of the function phi of x. So let it be arbitrary function. I will call it maybe g of x. The norm of g of x, a continuous function on the interval x1, x2 can be introduced as follows. The norm, I will not write it. So it's the maximum of the absolute value of g of x when x belongs to x1, x2. So this is the definition of the norm. Okay, so now we have the inequality, which is the following: for any x from x0 to x0 plus x0 plus h, we have the following: the absolute value of x1 of x minus phi2 of x less than or equal to L, this is the constant, times the integral from x0 plus h of phi1 of s minus phi2 of s ds. Okay, since this is true for any x, then we can see that the norm, so it follows that the norm of phi1 minus phi2 on this segment is less than or equal to L times the integral from x0 to x0 plus h of phi1 of s minus phi2 of s ds. Okay, and this is less than or equal to L times x0 plus h of the norm of the functions f1 minus phi1 minus phi2 ds. But this is a constant, and so this integral is equal to L times the norm of phi1 minus phi2 times h. Okay, so we have the inequality, the following one: phi1 minus phi2 is less than or equal to L times h times the norm of phi1 minus phi2 okay, and now so I assumed that there are two different functions, phi1 and phi2, satisfying our initial value problem. I promised to show h for which the function is unique. So now I can choose h as I want, and I want to take h to be equal to 1 over 2, so to the minimum value, so a minimum value of m1 1 over 2L to L, and a, because h should be less than a. If h is equal to the minimum of these two values, then we have the following: the norm of phi1 minus phi2 is less than or equal to 1/2 times the norm of phi1 minus phi2. And so this is a contradiction. So this inequality can be satisfied only when, so if and only if phi1 equals phi2 on so just a moment. x belongs to a segment from x0 to x0 plus h. So I have shown how to choose h so that we can guarantee the uniqueness of a solution. So this contradiction proves that a solution is unique if it exists. So theorem is proved. And now I think let's have a break.